So hello everyone, welcome back to last lecture of this NPTEL lecture series on cycloaddition reaction. So in this lecture what we will do is to try to summarize what we have discussed in the last 19 lectures. In lecture 1 we started with the classification of organic reactions. So then we moved to the pericyclic reaction, how pericyclic reactions are classified, and then we talked about cycloaddition reaction, how cycloaddition reactions are classified, like intermolecular, intramolecular, then type 1, type 2, that is for intramolecular Diels-Alder reaction, then for normal Diels-Alder reaction, that is normal 4+2, where the electron demand is normal, where that means you have electron donating substituent at the diene and electron withdrawing substituent at the dienophile. So then we also talked about the opposite of normal 4+2, that is inverse electron demand, where diene has electron withdrawing substituent and dienophile has electron donating substituents. The third one is the hetero 4+2 cycloaddition reaction, where the heteroatom can be part of either diene or dienophile, or sometimes it can be present in both. Then we also discussed about what are the various requirements of diene and dienophile to undergo Diels-Alder reaction. For example, in the case of diene, the diene should be in S-cis conformation, then only it can undergo Diels-Alder reaction. The S-trans conformation cannot undergo Diels-Alder reaction. And we also briefly touched upon the stereochemical outcome in the first lecture, but in the lecture 2 we discussed this in details. Particularly we talked about when you have the diene in the plane and the dienophile, if it approaches from the top face of the diene and bottom face of the diene, how the product will be and why the Diels-Alder reaction, if it does not have a chiral component, why it gives racemic mixture. This we discussed in details. We also talked about exo and endo concept, and for that I briefly talked about the Q model, where the top, the 4-membered ring, you put the diene, and in the bottom 4-membered ring you put the dienophile, then you do the Diels-Alder reaction, and that will give you better idea to visualize how the endo product is formed during the Diels-Alder reaction. And here is another simple illustration of how a reaction between cyclopentadiene and benzoquinone can be easily visualized through such transition state to write the endo product. So we also discussed several examples of 4+2 cycloaddition reaction, and for example, when you take like this diene and then dienophile, you can see that the product which you get is racemic, but it can be chiral if you use any chiral ligands or catalysts. In the lecture 3, again we continue upon stereochemical outcome for some time and move to the regiochemical outcome of 4+2 cycloaddition reaction. So for example, if you have a diene with substituent at carbon number 1, then the Diels-Alder reaction you will get 1,2 cycloadact, and if you have the substituent attached to diene is at carbon number 2, then you will get predominantly the 1,4 adduct. Then we also talked about Danishevsky's diene and Raval's diene, where the electron donating substituents are present in carbon number 1 and 3. This is Danishevsky diene, and this is Virech-Raval's diene, and we also discussed how these dienes have been successfully used in total synthesis, and this is one intermediate where Raval's diene has been successfully used to make this intermediate in only 2 steps. And for example, if you take 1-methyl butadiene and then treat with 3-nitrocyclohexenone. Here between the carbonyl group and the nitro group, the nitro group will determine the regiochemical outcome of this Diels-Alder reaction. So that also we discussed, and then we discussed about various applications of Danishevsky diene in 4+2 cycloaddition reaction. In lecture 4, so we talked about the applications of 4+2 cycloaddition reaction with particular emphasis on regiochemical and stereochemical outcome. We talked about synthetic route to be porphyrin and this particular dienophile. So when you take this dienophile, you see that there are 2 double bonds which in principle can undergo Diels-Alder reaction, and there are 2 carbonyl groups which can be considered as electron withdrawing group. So accordingly you will see the regio and stereochemical outcome of this Diels-Alder reaction, okay, and how selective this particular reaction has been successfully used in the total synthesis of gibberellic acid by E.J. Corey. Then we moved on to discuss about various synthetic equivalents in Diels-Alder reaction, because some of the dienophiles we cannot use directly. For example, ketenes cannot be used directly as a dienophile in Diels-Alder reaction. So you have to use some synthetic equivalents. So for example, we used alpha chloracrylonitrile and nitroethylene. So these 2 were successfully used in Diels-Alder reaction as ketene equivalents, and phenyl vinyl sulfone has been used as ethylene equivalent, and phenyl vinyl sulfoxide has been used as acetylene equivalent. So in lecture 5, we talked mainly about inverse electron demand Diels-Alder reaction. So as I said, in a normal Diels-Alder reaction, electron donating group is attached to the diene and electron withdrawing group is attached to the dienophile. Here it is reverse. As you can see here, there are 2 electron withdrawing groups attached to the diene and 1 electron donating group attached to the dienophile, and how this inverse electron demand Diels-Alder reaction works, and we discussed a few examples. And here also you can see there is a sulfoxide which is electron withdrawing, whereas here you have an enamine which is the dienophile, and that gives this interesting tetracyclic compound. Then we also moved from inverse electron demand Diels-Alder reaction to hetero Diels-Alder reaction, where heteroatom is part of the diene and heteroatom is also part of the dienophile. So and we also discussed a few examples where heteroatom is part of the diene and dienophile. In the 5th lecture, we continued this hetero Diels-Alder reaction, and then we discussed several examples, and in this particular example you can see this Diels-Alder reaction also leads to the pyridine, highly substituted pyridine, and in some cases the dienophile, heterodienophile were generated in situ. For example, NO is generated in situ by treating with sodium peroiodate, so that underwent 4+2 cycloaddition reaction. And in some cases we also have discussed where ozonolysis or osmium tetroxide cleavage of diol gives this aldehyde which undergoes an intramolecular 4+2 hetero-Diels-Alder reaction to give this tricyclic compound. Then in lecture number 6, we talked about what is intramolecular Diels-Alder reaction, what are the various types of intramolecular Diels-Alder reaction like IMDA type 1 and IMDA type 2, and in this particular lecture we talked mainly about IMDA type 1, where the dienophile is attached to carbon number 1 of the diene, so that gives the fused bicyclic compound. And when you have an electron withdrawing carbonyl group attached to the dienophile, so then in the final outcome you can see you get cis isomer, and same thing if you don't have the carbonyl group, and that gives the trans isomer. We also discussed the transition state leading to both cis and trans isomers in these two reactions. And we also discussed about heterodyl salt reaction, for example, acyl nitroso compound which can be prepared in situ that can undergo an intramolecular diel salt reaction type 1 with this diene to give such bicyclooxazinolactates. In the next lecture, we moved on to IMDA type 2, so which is nothing but where you have the dienophile attached to carbon number 2, and that upon heating gives a bicyclic compound, and this bicyclic compound is nothing but bridged bicyclic compound. And we also discussed several examples. Now you can see it has 4-4-3-1 system, and we also discussed 5-5-3-1 system. So this is a very interesting example where it is heteroatom, that is imine is the dienophile in the type 2 intramolecular diel salt reaction, and we also discussed the bis intramolecular type 2 diel salt reaction. So this is an example. The first one is type 1, and the second one is intramolecular type 2. And in this particular example, we also discussed the tethering through silicon. We also discussed tethering to magnesium, tethering to oxygen. Finally, after the diel salt reaction is over, you can cleave the silicon or you can cleave the magnesium and oxygen to get only monocyclic compound. In lecture 8, so we talked about retro-diel salt reaction. We know what is retro-diel salt reaction. You take a diene and then do a diel salt reaction first, and that gives this intermediate. This upon further heating, it undergoes elimination of a stable group. Here the stable group is acetonitrile, so leading to this tri-substituted furan. So this type of retro-diel salt reactions are very useful in making new types of aromatic compounds. Then we discussed in details about Alder-Rickert reaction, where a cyclic diene upon diel salt reaction with dimethylacetylene dicarboxylate gives such bicyclic compound. So now this upon further heating can undergo again like retro-diel salt reaction elimination of ethylene to give aromatic compound. So this is another interesting method to make polysubstituted aromatic compound, where you start with a cyclic diene, treat with dimethylacetylene dicarboxylate, followed by further heating, you get the Alder-Rickert reaction product. Then we also discussed about dihydro-diel salt reaction, where if you have an E9 and a triple bond, here you can see this E9 will act as a diene, so that will undergo 4+2 cycloaddition with this triple bond, and you get this compound that undergoes hydrogen shift to give this naphthalene type derivative. And in lecture number 9, we talked about use of Lewis acid in diel salt reaction. As you know, when you use Lewis acid, so the Lewis acid actually brings down the HOMO-LUMO energy gap between the diene and dienophile. That is how the Lewis acid, when you use, the diel salt reaction can be done at very low temperature, sometimes as low as -78, one can do the diel salt reaction. So for example, you can take a diene and then treat with substituted acrolein and use of Lewis acid like methyl aluminum chloride, you can do this reaction at 0 degrees to get this substituted cyclohexene. And in this particular example, the use of oxime and Lewis acid actually changes the regiochemical outcome. If Lewis acid was not used, you get exactly opposite regiochemistry, because the use of tin tetrachloride, which coordinates nitrogen and oxygen, so makes this double bond more reactive towards the diel salt reaction with butadiene. Otherwise, you can see this carbonyl group will determine the regiochemical outcome of this bond. So then we move to asymmetric diel salt reaction, where chiral auxiliaries, chiral ligands have been successfully used in asymmetric diel salt reaction. We talked about the use of 8-phenyl menthol reported by E.J. Corey in asymmetric Diels-Hall reaction. Then we talked about use of chiral oxazolidone reported by Evans in Diels-Hall reaction. As you can see here, the bulky group in the bottom phase actually blocks the approach of the diene coming from the bottom. So, diene comes always from the top phase. That is how one enantiomer is preferred over another enantiomer. Of course, when you do this reaction with chiral auxiliary, you get a diastereomer, but diastereomer, after removing the chiral auxiliary, you will get one enantiomer. In lecture number 10, we started with a brief introduction to 1,3-dipolar cycloaddition reaction, and then we also discussed about various 1,3-dipoles which could be potentially used in 1,3-dipolar cycloaddition. And in this particular lecture, we focused only on ozonolysis or ozone as dipole in 1,3-dipolar cycloaddition. Say for example, if you have a double bond, this upon ozonolysis followed by oxidative workup, you get the dicarboxylic acid, and of course this anhydride also will get hydrolyzed to dicarboxylic acid. So overall you get a tetracarboxylic acid. And another interesting example where you have alpha beta unsaturated ketone, when you do the ozonolysis followed by oxidative workup, you get ketocarboxylic acid, and in the process you can see one carbon atom is lost. So then we touched upon Craig rearrangement. So Craig rearrangement is nothing but if you have a double bond and then after ozonolysis and then treatment with acetic anhydride, it forms this type of peracetate, and that undergoes further rearrangement to give hydroxyl group. Basically you can see what happens, this 2-propenyl group is replaced by OH group. So this Craig rearrangement is known to remove 3 carbon unit as in the case of carbon and replace it with OH, and what is important is the retention of stereochemistry. The 2-propenyl group in this is alpha, and then hydroxyl group also is alpha. So in lecture 11, we moved from ozone to nitrones, how nitrones can be made. So there are several methods one can make nitrones. Just I would like to recall. So if you have a leaving group at appropriate place, then the lone pair on the nitrogen of the protected oxime can intramolecularly attack and then form nitrone when it is treated with tetrabutyl ammonium fluoride. So this is one of the important methods to make sugar derived cyclic nitrone. Or if you have substituted hydroxylamine, treat with aldehyde, so that in situ can generate nitrone, which is acyclic nitrone. And if you have proline or any amino acid, that upon treatment with sodium tungstate and hydrogen peroxide, it can generate nitrone. And if you have the hydroxypyrrolidine, and if you treat with mercuric oxide or any other oxidizing agents like IBX and so on, that also can give the corresponding cyclic nitrone. So after discussing various methods of preparation of nitrones, then we move to how these nitrones are successfully used in 1,3-dipolar cycloaddition. We discussed few examples of nitrones being used in intermolecular cycloaddition reaction. So then we also talked about the intramolecular 1,3-dipolar cycloaddition of nitrones giving such nice polycyclic compound. Then in the case of intramolecular 1,3-dipolar cycloaddition, so this nitrone and alpha beta unsaturated ester will give this bicyclic compound. Now if you cleave this NO bond, so you will get the corresponding amino alcohol. Then from nitrones we move to carbonyl ylides. So carbonyl ylides are easily made if you have a carbene and if you have a carbonyl group. So it can be from the same molecule or from the different molecule, it can lead to such carbonyl ylides. So this is intermolecular formation of carbonyl ylides, whereas in the next case you can see you have a carbonyl group and the diazo compound. You can treat with a dirhodium tetraacetate or copper acetate. So basically you generate a carbenoid, metal carbenoid, in this case sodium carbenoid. So that is, that can in principle generate these carbonyl halides, so which in turn can undergo dipolar cycloaddition with various dipolar like naphthoquinone, alpha beta ancetral ester like methyl acrylate, and sometimes you can see such carbonyl halides can also undergo very interesting intramolecular 1,3 dipolar cycloaddition to give such tetracyclic compound. Then we also touched upon azomethane halides. So azomethane halides are of 4 types. One is W shaped and the second one is U shaped, and the third and fourth one are S shaped halides, and how these azomethane halides are successfully used in 1,3 dipolar cycloaddition. That is what we discussed in lecture 12. And we also continued that a little bit in lecture 13 with some selected examples, and here in this case you can see this trimethylsilyl group can be easily cleaved under fluoride treatment, and that followed by 1,3 dipolar cycloaddition with 1 dimethylacetylene dicarboxylate, and followed by loss of TMSOH, one can get a tetra substituted pyrols, which are not that easy to make. Then from azomethane halides we move to nitrile oxides. So nitrile oxides are easily prepared from aldoxymes as well as nitroalkanes. So aldoxymes upon treatment with chlorine or NBS or NCS and followed by treatment with base, it gives nitrile oxide. One can also prepare the same, as I said, from nitroalkane by treating with a dehydrating agent. So these nitrile oxides are known to undergo 3+2 cycloaddition, and followed by treatment with LAH, one can get 1,3-amino alcohol. You can reduce it with hydrogen or hydrogenolysis followed by NO bond cleavage, also can get the same thing. In lecture 14, so we move to a very important class of dipole, that is azides. So how azides are used in 1,3 dipolar cycloaddition, particularly with alpha beta ancetral system, and when the same reaction was carried out between azide and alkyne, it normally gave a mixture of 1,4 and 1,5 triazoles. However, with the advent of using copper sulfate and sodium ascorbate or copper iodide and diisopropyl ethylamine developed by Sharpless, one can get only 1,4 triazoles, and many 1, 2, 3 triazoles have been made using this click chemistry. For example, if you have amino azides derived from amino acids, and the alkynyl ferrozine can undergo 1,3 dipolar cycloaddition to form this 1,4 triazole. So then in the 15th lecture we talked about 4 more dipoles: diazoalkane, nitrile amines, azomethanes, and nitrile halides. For example, when you use a diazo compound, it gives pyrazolene derivative, and when you use nitrile amines, you can use either double bond or carbonyl group, so it can give this interesting 5-membered ring. And when you take an aldehyde and treat with monoprotected hydrazine, it in situ generates this azomethane, and that can undergo an intramolecular 1,3 dipolar cycloaddition with a double bond to get this interesting tricyclic compound. So the last one is nitrile halides. This is nitrile and then this is halide. So this can undergo a 1,3 dipolar cycloaddition, and this is the major product in such 1,3 dipolar cycloaddition reaction. In lecture 16, we moved from 1,3 dipolar to 2+2 cycloaddition. So we talked mainly about thermal 2+2 cycloaddition, which is not that common, but it is because of the use of ketene, allene, isocyanide. So here the use of diketene derived from trichloroacetyl chloride gives this 2+2 product under thermal condition, and yes, the stereochemical outcome of 2+2 cycloaddition was also discussed in details. When you take dicyclopentadiene and ethyl ketene, so it gives exclusively the endo-cis product, and if you take cyclopentadiene and this isocyanide, so this double bond reacts to form this bicyclic lactam. And we also discussed about the dimerization of allenes to get this monocyclic compound. And when you have an allene and if you add H plus or HCl, one of the allenes will react to give this cation, vinyl cation, and this vinyl cation can undergo 2+2, give this cyclobutyl cation, which will be quenched with chloride to give 1,4-dichlorocyclobutane. In lecture 17, so we moved from thermal to photochemical 2+2 cycloaddition reaction. So we started with brief history of photochemistry and what are the earliest 2+2 cycloaddition reported under photochemical condition, like cinnamic acid to alpha terephthalic acid, beta terephthalic acid. So they are obtained by head to head and head to tail 2+2 cycloaddition mode, and intramolecular cycloaddition with Lewis acid like copper triflate, which actually helped in carrying out this 2+2 cycloaddition reaction more efficiently. And we also used a sensitizer like acetone to facilitate the dimerization of alkanes like norbornene. So then the intramolecular 2+2 cycloaddition, how such intramolecular 2+2 cycloaddition reactions have been successfully used in the total synthesis of triquinanes. And here in this case the 2+2 cycloaddition between the allene and the double bond gives the substituted pyrols. In lecture number 18, we talked about the total synthesis of cubane, where two important reactions have been successfully used in the total synthesis. One is quasi-Favorsky reaction, two is intramolecular 2+2 cycloaddition to get this very ring-strained compound, and that was then converted into cubane in few steps. And we also talked about de Mayo reaction, where the cut and paste chemistry successfully used through 2+2 cycloaddition followed by retroaldol, and that diketone also can undergo an aldol reaction to give another 6-membered ring. So then we talked about Patton-Bucchi reaction, where you have a carbonyl group. The carbonyl group can undergo 2+2 cycloaddition with an alkene or alkyne, and it can also undergo an intramolecular 2+2 cycloaddition between alkene and carbonyl group. So that will lead to oxetane, and this particular method has been successfully used in the total synthesis of many triquinanes by Weierich-Rabel. In lecture 19, so we talked about various rules which are followed for predicting the stereochemical, regiochemical outcome of dipolar cycloaddition, not only regiochemical and stereochemical outcome, but also predicting about whether these reactions are thermally allowed or photochemically allowed. So three such rules we discussed. The first one was reported by Zimmermann and Dewar. So they used the aromaticity approach. The second one was again developed by Woodward and Hoffman, that we discussed in details about the use of FMOs, that is frontier molecular orbital, that was further developed by Fuchs. And in the last one we talked about the orbital symmetric correlation between the starting material and the product, and this was developed by both Woodward and Hoffman. So we call it as Woodward-Hoffman rules for the conservation of orbital symmetry. So what we have done in this course is to give overview, as well as we also discussed several interesting examples of various cycloaddition processes known in the literature. Particularly we focused only on three different cycloaddition reaction. One is 4+2, second one is 3+2, and third one is 2+2. As you know, these three are the common cycloaddition reaction which you will encounter. The 4+2 will give 6-membered ring, 3+2 will give 5-membered ring, and 2+2 will give 4-membered ring. So, what you should do now, periodically go through all the assignments carefully and then try to solve. So, then if you have any doubts, please feel free to ask us through email or whenever our TA discusses with you, you can ask him directly. And for the exam, go through all the lectures, and we have discussed several examples, and if you understand the concepts discussed during these lectures, you will be able to answer all the questions which will be coming in the exam. Okay. So, now I wish you all the best for successfully writing the exam, and also successfully using whatever you have learned in this cyclodation reaction in your future endeavors. Thank you.